Okay, I think I'll start here talking about two-dimensional vectors and vector arithmetic. I'm going to write a 2D vector in the component or coordinate form, and as a linear combination of standard unit vectors. And then I'm going to write the vectors in terms of magnitude and direction angle in a standard position. So let's start off. We're talking about two-dimensional vectors. So we'll use a notation like this. V is a vector, and this coordinate form, I just mean something like this. Right now two-dimensional, so it just has an x and a y component. We'll draw a picture. I'll start this one with A and B both positive. So there's a point with parentheses. You see I use parentheses for the point in two-dimensional space. And then since I'm talking about vectors, I have that arrow, so it has some magnitude and direction, this vector V with these components A and B. Now, we can say this can also be written as, let's do this in a kind of slow, fancy way here. It's the sum of these two vectors. And these two vectors, I could factor out this scalar value A and say this is 1, 0. This is B times 0, 1. So now I've turned these into scalars. A and B are scalars. Of course, they were scalars from the beginning. It's the combination of those two scalars, A and B, that form this vector that has several scalars combined together to have this meaning of a direction. This 1, 0 vector is a particularly important vector that I'm going to call I. And I'll put a little symbol like that to indicate that it's a vector that's a unit vector, that's a length of 1, and it's a special unit vector. And the fact that it's a unit vector is why I use this little hat notation. You don't really have to do that. It's just something I picked up somewhere that other people do as well. It's to sort of distinguish the unit vector as being different than a just general vector that has the arrows. So A times the unit vector I, and B times the unit vector j, which this is the unit vector j, 0, 1. So what I'm really saying is that if I was this vector, and j is here, this vector, then I could say multiply I by the scalar value A, and it produces a longer vector A times I, add B times the unit vector j, and you have this vector that we could imagine being here, and it's the sum of the two that form the vector V. So it's the sum of these two vectors that form this vector V. So that's what we mean by a linear combination of standard unit vectors, the I and the j being my standard unit vectors. You could form other unit vectors, of course, but I and j, and later when we're in 3D, k, of course, are the standard unit vectors. And one other thing that we could do here is to describe this magnitude and direction in terms of a number, a scalar magnitude, and a direction theta. So let me draw the picture one more time. Well, I think I can do this. I just wanted to put theta into my triangle there as a angle in standard position. And when I say standard position, what I'm talking about is measuring positive angles counterclockwise from the x-axis. That's standard position. So we could begin to develop a alternate form for a two-dimensional vector by using some trig. We'll say that the cosine of theta is A over the magnitude of V, and we could say sine of theta is B over magnitude of V. So we could write A is magnitude of V cos theta, and B, magnitude of V sine theta. And so with that, I could say if V is A times unit vector I and B times unit vector J, then it's also magnitude of V cos theta times the unit vector I, which has nothing to do with the complex number or imaginary number I. This is just another use of the letter I. Plus, now B is magnitude of V sine theta, and we have this unit vector J, and it's common enough to write the magnitude out front separately. So this is one other very important form for writing two-dimensional vectors. And it'll be neat to see later, we go a little bit further into three-dimensional vectors, how we'll use, we could really just use two, but it's just more natural and easy to go to three angles once we hit 3 dimensions, to use 3 different angles for the direction. Here we only need one when we're in 2 dimensions, because once you have the angle theta, that uniquely determines the direction. There is another angle that we could have used to write this, both of these in terms of cosines, and that's precisely what I'll do when I go to 3 dimensions, but it just works perfect to say, for this vector v, all you need is a magnitude and an angle, and that uniquely defines the direction. Sometimes I get kind of lazy to write the arrow if I have the magnitude symbols, because if I have the magnitude symbols, it's clearly a vector. You see, I didn't do it in these other places because it's my habit not to do that if I recognize that it's a vector because I have indicated magnitude. Okay, so let's look at an example. Given the vector -4, 3, write in the form magnitude v cos theta I plus sine theta j. So first we need the magnitude. Well, we could do either one first, but I'll do the magnitude first. That's the easiest thing, and it comes right from the distance formula. I'm really finding the distance from the origin to the terminal point, and that's an easy one. Magnitude is exactly 5. But to find the angle, maybe I'll just do a little bit of theory here, and start with a simple case where it's in the first quadrant. Let's say we're back to a point AB for some vector in general. We have some angle theta that we're going to try to find. So we have a side A and a side B. And the crucial thing that I want to say, well, let's call this vector V again. I could say magnitude of V is the square root of A squared plus B squared. And then to get the angle, I could start with the tangent of theta is the opposite over the adjacent. And from there I could find theta as the tan inverse. And the useful thing about this is that this really does work for any B and A values in general if you include for the restriction on the definition of the tan inverse. So the definition, so if the angle happens to be in any other quadrant, we'll have to correct for it. It's always a matter of adding 180 degrees because of the period of tangent is 180 degrees, and it's in that way that we could correct for this restriction. So if we go back to the example we're looking at, you see it's actually in the second quadrant. So I write parentheses to indicate the point, the terminal point, and I use these brackets to indicate a vector. And we know the magnitude is 5. And this is a -4 here in this direction, and this is a +3 in this direction. But the angle is not here, really. The angle that we need is this one. And so when we use the tan inverse, you do the B value over the A value, you're going to get about -36 0.9, and it isn't exactly, so we'll have to round off. There is no exact whole number angle that produces these sides of a 3, 4, 5. So now, the trouble with this is because of the restriction on the angle for the tan inverse, what the calculator is doing is producing this angle, negative 36.9 here, which is not the correct angle to locate that position if you put the angle in standard position. So what I have to do is say this is really not theta, this is theta prime, and the actual theta is 180 degrees clockwise rotation from there. So it's 180 plus the negative 36.9 degrees. And that's 143.1. And so that's the angle that I actually need to write it in that correct form, or in that form that was required. So the vector negative 4, 3 can be written as 5 cos of 143.1 times unit vector I and sine of 143.1 times unit vector j. And that's it. And you could check. You could use the calculator to do cosine 143.1. Multiply by 5 and you'll get something really close to negative 4. It won't come out exactly negative 4 because we didn't actually have the exact angle, but you could make it more and more accurate by using more and more accurate decimal approximation to the angle. So that's it. All right, let me see if I can fit one more example in here. A plane intends to fly 400 miles an hour directly east. However, there's a constant wind from the northwest at 50 miles an hour. It's a pretty strong wind, but anyway. Determine a velocity for the plane that, when combined with the wind, will result in the desired velocity vector. Write the answer in terms of required speed and direction, that is the magnitude of the vector and an angle measured from north. So let's record some of the things we have. Maybe we could start off with the velocity that we want is 400 times the unit vector I. You start with a picture too. So if what I want is a vector that looks like this with a magnitude of 400, I'll now think about this wind from the northwest. So let's take north up here and west out there. So the wind, since it's from the northwest and it doesn't really say anything more, we'll have to just assume equally north and west. And that means really at a 45-degree angle out of this corner. So here's the west, here's the north, here's east, south. So this is the wind. Now the useful thing about a vector is that it contains both a magnitude and a direction. So we know this is a magnitude of 50. We know that it's coming from the northwest, so we have a direction. But that doesn't mean you have to necessarily draw it here. And actually, in order to work with these two vectors in the same sort of coordinate system, it'll be helpful to put this wind vector here so that I can think about what angle theta I need to describe that. So to measure the angle in standard position, I'm going to use theta equal negative 45. There are other options. You don't have to use negative 45. You could use 300 and that puts me at 315. That's another option. You could use 315 degrees. But negative 45 is an obvious choice. So the wind, it has a magnitude of 50 cosine negative 45 sine negative 45. Okay, so what I've done here is take the magnitude of the wind, 50, and multiply by this unit vector that points in the direction from the northwest, right? That was the direction in which the wind was blowing directly out of the northwest. So with this angle of minus 45 degrees creates this unit vector. distributing the 50, I get these two terms for components of the wind vector. And now we can move on to answer the question. We want to find this corrected velocity that the plane needs to fly at to account for the wind to achieve the desired velocity, that's this vector v. So if you take the wind, that is the wind plus the velocity of the airplane, the corrected velocity of the airplane, together those two should make this desired velocity at 400 directly east, 400 miles an hour directly east. So solving for the necessary velocity, c, we'll have c is v minus w, or the velocity we want without the wind. And then doing that subtraction, here's the target velocity that we're trying to get, 400, 0, minus the wind, distributing the negative and combining the components. The x components are 400 minus 25 root 2. And then the y component, the negative distributes, that gives me 25 root 2. And simplifying that, in putting it in decimal, gives me 364.6 and 35.4 for the x and y components of this 2D vector that the plane would need to fly at. It's indicating both magnitude and direction in that vector, but it isn't the final form that I want the answer to be. Well, so the thing that I could do at this point is I could figure out the magnitude of that corrected velocity, which is in fact the speed being the magnitude of the velocity. So it's the square root of that 364.6 squared and 35.4 squared. So this is like, it's the speed. And the other part would be the angle from north. So I'm going to try to figure out, first of all, the angle just measured from, actually it'll be from east because it'll be the angle in standard position. So that would be theta is tan inverse of the b value over the a value. So it's actually, and both of these are positive, so I don't really have to worry about correcting for the quadrant. This comes out. Now I'm going to put it in degree mode. You could write it either way, but being a practical word problem, very often degrees is a more practical way to state your answer. So what we're really looking at is this really long 364 units and 35.4 units. And this is the velocity that the plane needs to actually fly at to compensate for the wind, so that the wind pushes it back to the desired velocity, right? This is the vector that we just found, and the 5.5 is this, but not quite my answer. I really want this guy. Then we could call that the bearing, right, from north. Well, just knowing that theta is an angle in the first quadrant measured in standard position, positive being counterclockwise, from that understanding, that's where I make the conclusion that I have to take 90 minus the 5.55. All right, so then we'll take 90 degrees minus the 5.55 degrees and get 84.45 as the bearing, that is the angle measured from north. So our final answer is fly at a speed of 366.3 miles per hour at a bearing of 84.45 degrees from north. All right, that's the end of the video. I hope this was helpful.